So chapter 6 is about thermochemistry. So thermo reminds us of heat, and so this is about heat, but more importantly about the energy involved in chemistry. So chemical hand warmers. Have you guys ever used these? Those little pouchy things, and you squish them around, and then they just like get warm. Magic, no electricity required. Most of these work using a slow oxidation of iron. So iron reacts with oxygen and forms iron oxide. How much heat you get out depends on the size of the hand warmer, the size of your hand or your glove or whatever it's in, but mostly the amount of heat that's released by the reaction. So some reactions will release a lot of heat, some release very little heat, some reactions actually absorb heat, so that would not be good as a hand warmer. The universe is composed of matter and energy, and so we can't just look at matter because they interact with each other. So what is energy? And we use that word a lot. I've got actually an energy drink right here. Does that have energy in it? What is energy? Energy is the capacity to do work. Not that it's doing the work, but it's the capacity to do work. So then what is work, right? I have to keep defining things. Well, in science we define work, and this is really more physics. Work is a force acting over a distance. So energy is the capacity to do work, which equals force times distance. So like there's this wash bottle with soap sitting on the counter. If I push that across the counter, I applied a force through a distance, I did work on that soap wash bottle. So that's energy. Heat is not the same as energy. Heat is a flow of energy, specifically caused by a difference in temperature. So heat is when energy flows from something that's warmer to something that's cooler. Energy can be exchanged between objects through contact. An example is through collision. Two objects collide and energy can be exchanged. So think of energy as a quantity that can be possessed. Heat and work are ways in which energy can be exchanged. Energy can move in or out of an object. So energy is something that an object has, and heat or work are ways that the energy is transferred or exchanged. So different kinds of energy. Kinetic energy is the energy of motion. So something that's moving has kinetic energy. And we talked about this a little bit when we talked about gas particles and their average kinetic energy and the relationship between the mass and the velocity. Thermal energy is energy associated with temperature. Thermal energy is actually a form of kinetic energy. We've talked about we've talked about temperature as a measure of the average kinetic energy of a substance. And hopefully we understand that all atoms and molecules are moving, okay? So you are in the solid state of students right now, and you're all moving a little bit, right? A higher temperature would mean you're moving more, like you're getting really antsy and you're jumping around in your chair. You have more kinetic energy. Higher temperature, more thermal energy. So thermal energy is a form of kinetic energy, but it doesn't necessarily involve particles moving through space, but they might be just moving around within a small space. So here we've got energy due to motion. The cue ball coming at this purple ball. When the cue ball hits that purple ball, there's an energy transfer that occurs, and the cue ball does work on the purple ball. The cue ball has stopped now, and the purple ball now has the energy in the form of kinetic energy and moves off. So there's been a transfer of energy from one ball to the other. So kinetic energy is movement, motion. Potential energy is energy stored in an object or energy due to the composition and or position of an object. The relevant form of potential energy for chemistry is referred to as chemical energy, and this is a potential energy due to the relative positions of electrons and nuclei within the atoms and molecules. Here we have an example of gravitational potential energy. If you hold that ball above the surface of the table, it has potential energy. Because if you let go of it, what's going to happen? It's going to fall, right? You can do that with a Sharpie. If I hold the Sharpie out, it's got potential energy because when I let go of it, it falls to the floor. As I let go of it, it began to move and it got lower and lower. It got less potential energy as it got closer to the floor, but it had more kinetic energy because it went faster and faster until it hit the floor. So this is sort of a summary of these ideas about energy. So energy is the capacity to do work. We've got kinetic energy due to motion. Thermal energy is a form of that. It's the motion of the particles. So temperature is an average kinetic energy of the particles. This is a type of kinetic energy. Potential energy due to position or composition. Chemical energy is a type of potential energy associated with positions of electrons and nuclei. We have positive and negative charged particles inside the atoms, and their positions cause potential energy. Anybody have any questions? Just some examples of forms of energy. Electrical energy. If you've ever stuck your finger in an electrical socket or been shocked by a frayed cord, is there energy there? Yeah. So electrical energy is a form of kinetic energy due to the flow of electrical charge. So electricity is the flow of electrons. So the electrons are moving, and so that's a form of kinetic energy. Heat or thermal energy we just talked about that. That's kinetic energy associated with molecular or atomic motion. Light or radiant energy, if you go out and stand in the sun, is there energy coming from that light? Yeah. You get really hot standing in the sun, right? That's a form of kinetic energy. And that has to do with energy transitions within atoms. So the sun has kinetic energy due to transitions within the atoms in the sun, and those are releasing this radiant energy. Nuclear energy. This is a form of potential energy, and it's due to the structure of the nucleus. And chemical energy, also a form of potential energy. Here, this is due to the relationship, the attachment between atoms and molecules, the attractions between ions and an ionic compound, and so that's what chemical energy is. So energy is conserved. We've talked about conservation of mass. Energy is also conserved. So it's referred to as the law of conservation of energy. Energy can neither be created nor destroyed. So when you have energy being transferred from one object to another, you don't gain or lose energy in that. The total amount of energy is the same. But the form of the energy may change. Here we have an example of a woman pushing down on a ball that's sitting on a spring. So as she pushes down, she's giving mechanical potential energy by compressing this spring. When she releases the ball, the spring springs up and pushes the ball into the air. The mechanical energy stored in the spring gets transferred to kinetic energy, the movement of the ball. As the ball goes up, it slows down, but it's higher above the floor. Its potential energy is increasing as its kinetic energy decreases, and then it'll get to the peak and then it'll fall back down. So energy is constantly transforming and being transferred between objects. We just don't even recognize it. So when we're talking about conservation of energy, we have to define what we're looking at. Because conservation of energy applies to the universe. So in the universe, the amount of energy is constant. We can't look at the whole universe all the time. It's just not practical. So we look at smaller parts of it. And so the part that we're interested in, we usually refer to as the system. That's the material or the process that we're studying the energy changes in. So the piece of the universe that we're interested in, that's the system. The surroundings is everything else. And the only part we really, it's actually the rest of the universe, but the only part we really need to be concerned about is anything around it that it could exchange energy with. Okay? So we're studying the exchange of energy between the system and the surroundings. So if we have our system, our thing that we're looking at, and here we're just, using sort of like a gas gauge here to indicate how much energy is in it. So let's say the energy tank is half full of the system, and the surroundings is a quarter full. And then there's some energy transfer that occurs. The system has lost energy. The surroundings has gained the same amount of energy. The total amount of energy is lost. I find it useful to think of energy as being a lot like money, right? So in a financial transaction, one person loses money and the other person gains money. Is money created or destroyed in that transaction? No. The amount of money is the same, it's just transferred, right? And so it's the same idea here with energy. The amount of kinetic energy, as we mentioned in Chapter 5, is proportional to the mass and the velocity. So kinetic energy is 1/2 mv squared, the mass times the velocity squared. The SI unit of energy is the joule. This is a funny spelling. Capital J is the unit abbreviation. It's a relatively small unit, and so we often find it useful to talk about things in kilojoules. And here we're using the metric prefix the same way that we've used it with all the other units. Kilo means 1,000 or 10 to the third. So a kilojoule is 1,000 joules. And just for an idea of how much or how large a joule is, so we've got a picture of a light bulb here. This light bulb turned on for an hour would use 3.6 times 10 to the 5th joules. That's a large number. Joule is a very small unit of energy. We could also express that in kilowatt hours, so that would be 0.1 kilowatt hours, and that's the unit that the electric company uses. So how is a joule defined? A joule is the amount of energy needed to move a 1 kilogram mass a distance of 1 meter. So 1 joule equals 1 Newton times meter. So energy is the capacity to do work. Work is a force applied over a distance. So a Newton is a unit of force, and a meter is a unit of distance. So it's a force times a distance. So a Newton is also equal to a kilogram meter per second squared. So we put these two together and we get kilogram meter squared per second squared. All of the base units in the SI system are put together and taken apart into other units. So joule is defined in terms of these other base units in the SI system. A calorie, you guys heard of calories, right? Yeah, so we associate that with food, right? So a calorie is the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. So the relationship here is that 1 calorie is exactly equal to 4.184 joules. So a calorie is a little bit bigger than a joule, but still a pretty small unit. Now the calories you've probably heard about and maybe counted if you were trying to lose weight are nutritional calories. Those are big calories. They're actually kilocalories. Okay? This calorie has a capital C. Its abbreviation has a capital C. That is equal to 1 kilocalorie or 1,000 regular calories. Now this can be very tricky and confusing, and I may try to trick you with this on an exam. Okay? I've said a lot, I won't try to trick you with this. Here I'm warning you, on exam 3, there may well be a problem where you have to do a conversion involving calories with a capital C. The big C means it's a big calorie. So the big calorie is actually 1,000 of the little calories with the little c. Okay, and the good news is the exam is typed, and so you don't have to worry about my handwriting, whether it's big or little. So here's a couple of tables from your textbook. Here's some conversion factors. A calorie to a joule, we'll use that one a lot. So you might end up remembering that one. The calorie or kilocalorie to calories, you can do that just because you know what kilo means. Kilowatt hours probably won't come up on an exam. A kilowatt hour is 3.6 times 10 to the 6 joules. That might come up in a homework problem or something, but I don't ever remember that one. And just for information, general interest, these are the different calorie units and how these different things, how much energy these different things use. So if you were to run a mile, that would be 4.2 times 10 to the 5th joules, or 1 times 10 to the 5th calories, lowercase c. 100 calories, capital C, those are the ones that, you look at the candy bar, how many calories, or 0.12 kilowatt hours. And so you can see the different comparisons here. Anybody have any questions?